folks, this video tutorial is for people who are either new to 3D Experience or transitioning from the ABAQUS program to the 3D Experience Release 2022x. And the way it works is that the particular playlist where this video is a collection of problems that are available on YouTube and solved by others using the Abacus program, maybe in a step-by-step fashion. Most of them are like that. So I will try to retrace the steps that they take in their own Abacus video tutorial so that you can see the correspondence between how things are done in 3D Experience as opposed to Abacus. Uh, I'm sure you know that the native solver, FEA solver for 3D Experience, is actually the Abacus program. However, not all features are the same. Not everything is implemented, and the icons and the interface and pretty much everything in 3D Experience is different from what you see in the Abacus program. Now, the particular problem that I'm going to do, we'll talk about the specifics of it later on, but this video was also done, the same problem that we're going to do in this tutorial was also done with an analytical rigid surface, okay? However, here I will do it with the so-called rigid body functionality. And the reason I do this is that the analytical rigid surfaces are rather limited in their scope. For example, they can only be extruded surfaces or revolved surfaces, and the profile that you extrude and revolve are very specific type. In other words, should be a collection of lines and circular arcs, which are less than well, circular arcs are less than 179 degrees. Okay, so if you have anything that doesn't fit that property, for example, if the rigid thing that you want to use, maybe as an indenter, maybe as a punch, is not does not qualify for an analytical rigid surface, or maybe you imported another mesh from a different program, and you want to declare part of that to be rigid, a rigid portion of the model, then you have no choice but to do it with rigid body. There's a lot more that you can do in rigid body than can be done in analytical rigid surface. Now, this can be found in the interaction in the abstraction tab. In the abstraction tab, you can find these tools. The one in the middle was already done. Okay, we're going to do in this video the one which is rigid body. Now, the specific problem that I'm going to do is, and was already done with analytical rigid surface, is done by this professor at University of Alberta. It's a plate, and it has two holes in it. And in the two holes, there are two, think about it as bolts that are holding this in place, and you move the right-hand side by 10 millimeter to the right. Okay, so essentially contact is going to be established between these bolts and the plate, and we're going to assume that the bolt is actually rigid. These bolts are rigid. Now, the, 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 the video that is done in a step-by-step fashion by this professor uses the plane stress problem, okay, 2D plane stress problem, but there are no plane stress or plane strain elements and axisymmetric elements in the 3D experience. I was told that recently in release 2022x, axisymmetric models have been, or axisymmetric elements have been implemented, but anyway, no plane stress. The thickness of this in the depth direction is 200 millimeter. Now, because of symmetry, incidentally, uh, this professor has taken only a half of that. In my case, since I have to do three-dimensional elements, I have to take half of that and half in the depth direction. So 1/4 of the plate basically. Okay. Now, details are given here. Notice that when you use rigid bodies, you have to uh, mesh everything. Okay, so in this particular problem, I've meshed the plate. This is 1/4 of the plate with solid elements, brack elements, or swept elements, and the bolt. Because it's going to be using as a rigid object. Okay, I have done it with shell elements, and it's hollow. Although it really doesn't matter, I could have done solid elements or swept element for the bolt also, but I decided to use the shell. Now, the details of the sizes of both the solid and surface elements, shell elements are given here, and also remember, because you're meshing the bolt, it you have to have a property associated with it, and that property, which is right here, can be a dummy property, because after all, it's going to become rigid body anyways. But I have decided to use the steel property that is used for the plate. Otherwise, it could have been any material. Okay. Now, we will see. I'll do a few things here, and we'll come back to that later on. We'll come back to this screen later on. There's some documentation about rigid bodies on the online documentation. So I have, I cut portions of those and left it here. If you're interested, you need to go to the actual source and do it yourself. And this is a very good resource for knowing the difference between analytical rigid body versus the discrete, discrete, or what is called rigid block in 3D experience. It's related pertaining to ABAQUS, but it's still it's very good because you know that the software's native solver is actually ABAQUS. Okay, so let's go ahead and do this. I already, because we're dealing with two parts interacting with each other, I already created an assembly. This is an assembly. This is where I went. 3D experience and assembly design. I'm in assembly design list. So we're going to insert our first part. So put the cursor there, right click, insert, and 3D part. Let's give it a second. Okay, right here. So let me rename this thing to be, how about plate? So properties, I'm going to call this thing plate. Plate. Okay. And we're going to make it. So double click on 3D shape. Okay, and on the vertical plane here, I will sketch that rectangle with a hole in it. Let me dimension these. So this is going to be 200 millimeters, and this is going to be 45 millimeters. All right. Now we're going to make a circle there. Okay, so dimension, the diameter of that circle is 15. 15. And it's exactly halfway from the top and the bottom, and it's going to be 50 millimeter from the center of it to that vertical edge. Let me zoom in. So the distance from that center, which I think is right there, to that line is going to be 50 millimeters. So So there is basically the model for the plate. So we exit, and we're going to pad this thing because we are using solid elements. So let's go ahead to the part design, because right now I'm in generative shape design. You can see that generative shape design up here. So we're going to go to part design. That's where we find pad. So under essential, there's the pad, and I'm going to make this thing 100 millimeters. Remember, the thickness of that plate is 200. Thickness into the screen is 200. Because of symmetry, I'm using only half of that. Of course, we have to put the symmetry boundary condition on the other side. Okay, we will now apply our material. So let's go to the part, 3D shape, and under tools, uh, create a material there, and I'll call it plate material. Call it steel. Okay. Say all right. Okay. Plate material steel. Right click. Apply. I'm going to close this. Apply it to this part. And now we're going to input our properties. So double click on material line, structures, ABAQUS multiphysics, mechanical, elasticity, elastic, 200,000 megapascal, which is 200 gigapascal, of course, 0.3, and say OK. All right. We will now insert our second part. So put the cursor on the top line, right click, insert, another 3D part. Let me call this thing the bolt. So properties, right click, properties, call it the bolt. Okay. All right. And now we're going to make it. Because it's going to be a surface, I need to be in generative shape design. So you go to 3D, generative shape design. If I wanted to make the ball a solid object, then, oops, wait a minute, I think we were already there. Yeah. Yeah, we were already there. So double click on this. Actually, so let me see. Try it one more time. Generative shape design. Right there. Okay. So under, we were already there. So under essentials, on the YZ plane, right there, we will sketch a circle concentric with that, slightly different radius, smaller radius. So I'm going to draw a circle there. Okay. The diameter of that circle is 14.6 millimeters. Okay. Now, if you want to make these two concentric to each other, you can put dimension from here to the center of the other one, make it 0, or you can select this guy, control that guy, these two circles, and then you go to cancel that. Let me try it one more time. This circle, control that circle. Okay. Constraint, define the dialog box, concentric. This is my favorite way of doing it. So exit. Notice that they are concentric, as you can see. So exit, and then on the surface, we extrude it. Surface, extrude 120 millimeters. there. Okay, this is a surface. You can see it's hollow right there. Okay, good. Now I will also create a point at the center of the circle because I need a reference point later on. So under essentials, you go to point, you select that, change this thing to circle and sphere center, and then you select that circle right there. So it creates a point there, and we're going to use it as a reference point later on. Now we will use the same material that was done here, so we can say under tools, material browser, the same material which was here, right click, apply, you can close that, and you apply it to this part, and it's going to use it. Good. That's pretty much it. So let's go ahead to structural model creation. Select the empty FEM. Okay, and you wait for this dialog box to show up and make sure that you select the entire assembly, because these parts both are going to be participating in my analysis. Okay, so we say okay right there. Right. So first of all, under meshing, you click on meshing. There is a sweep 3D mesh. You click on it and select this part. And we decided to use 3mm size here with 3 layers through the length direction. 3mm size and 3 layers through the thickness. There we are. So this plate is meshed. We might as well apply the properties to it. So click on the properties tab. There's a 3D solid, and you can go and select the part body here, right there. You see that? Part body. Use part body. It selects the right material, and we say OK. Then we're going to go back to meshing tab, and we're going to use surface-based quad mesh for shells. So here, right there, surface quad mesh. Select that extrude, or it really doesn't matter. It is the part body. It doesn't matter from the second part. And then put 4mm mesh size and mesh, and there we are. Okay, and let's also apply the property for the shell. So on the properties, this is the shell section. You can select the part body. It picks the right material, and you have to thickness. I'll put a one dummy thickness of 1mm, because at the end of the day, this is going to be rigid. Whatever you put here is not going to be used. But if you put a 0 there, obviously it's not going to like it. Okay, that's pretty much it. Now, abstraction. Now remember, we did the same thing in the other video when I did analytical rigid surface. The next thing was to define it was in that video to define the analytical rigid surface. Here we don't have an analytical rigid surface. We have a rigid body, right? See, this was analytical rigid surface. That was the other video, rigid body. So it says, what is the support? Now the support is that pretty much you can select that extrude right there, okay, or you can select the face, but I selected the extrude. And for the reference point, remember I created that point here, that point. So we're going to use the reference point. And for details, right now it's going to be the default. And default, I believe, is Thai. To know what these things are, I suggest you go to the documentation. But for us, it doesn't matter because we just want to make sure that this guy is just stays put. Okay, so we say, all right. Now, we defined our analytical rigid surface here. You can see that. No, I'm sorry, not analytical rigid surface. What I meant was the rigid body, right there. And that takes care of what we need to do here. So we're now going to go to the structural model scenario creation, structural scenario creation. We use the finite element model that was created. Okay. Procedures tab, we are doing a static step. Okay, let's make a initial time of 0.1. This is a dummy time, and maximum, actually let's make this thing 0.01, and maximum time increment of 0.1. And notice that we have the geometric nonlinearity on. Okay. All right, let's go ahead and define our restraints. First of all, the bottom of this block is a planar symmetry. So we go to restraints. Here's the planar symmetry. The bottom is planar symmetry. We do the side, the back side, planar symmetry on the back. Okay, these two faces. This point, this reference point is clamped, so we can select the clamp. Select the reference point here or from the tree, it doesn't matter. And this end is subject to a translation to the right. So we go under load, translation, select that face, and in the direction Y, right here, 10 millimeters. 10 millimeters. Okay, good. The final thing that we need to do is to define the interaction between this bolt, the cylinder, and that block. So we go to interactions. First, we define it, surface-based contact. Okay. So there are different ways of doing it. I'm showing just one way, and let's go ahead. Let's go ahead here. Oops, under the bolt part, we can select the for the main surface. Main surface in the old days, it used to be called master surface. Okay, the green one. We're going to use that extrude. Okay, and for the secondary surface, which used to be called slave surface. So we hide this, we hide that. We go and select the interior of this hole, the surface there. Okay. Now, I want to show you something. Notice that there are two arrows here. They're pointing to each other on purpose. On purpose, I'm going to select this arrow. This one is dim. There's not much you can do. With this one, you can click on it. Notice that now it points up. Okay, it points up. Okay, say okay. All right, both of them were pointing up. Let's go back here, check it again. Under interaction, surface space, notice that they're both pointing upward. Okay, if I click on this, it's going to go. Oh, sorry. Here's what I did. It looked like that. I click on it, it gives you this, and then click one more time. Notice that they're pointing in the same direction. For the secondary surface and the primary surface or the main surface, they're both pointing in the same direction. And I will show you that this is going to cause a problem. Okay, you say, all right. And the nature of that interaction is contact, hard contact. So I clicked on the contact property. On the normal behavior, I select the specify normal. Yeah, specify normal behavior option, hard contact right there. Say okay. All right. So we are ready to run. Go to simulate. First the model check, a scenario model check. Then it's the simulation check. And finally, the run. Run means simulate. While this is doing the checking, I want to remind you again that there are different ways of doing these, selecting these surface-based, contact, the main surface and the secondary surface, etc. That's one way of doing it, the way that I showed you. Okay, this is gone. This is done, and now we're going to simulate, and we'll see something interesting here. Or at least it's interesting to me. This iterations tab is the equivalent of monitor in the ABAQUS program. If I click on it, I see the different time increments, whether they were successful or not, how many iterations it took to go through that time increment. And this is plot, which is the condensed version of the one on the right. Okay, let's check that. See that? This is beginning to show a table. This is what monitor in ABAQUS does. And if you see a plot, it doesn't give you all the details, but it gives you. So when this when this thing reaches 1, means that the analysis is done. So let me click on iteration for it. It's going to go fast. I could have used a bigger time increment also. Done. Going to be extracting the results. And there we are. You see, if you look at the displacement and you look at the final displacement, it is going through the cylinder. It has no respect that there's a cylinder sitting there, there's a bolt sitting there, which is supposed to establish contact and stop it. If you look at the stress, they're all going to be zero. Pretty much they're all zero. You can see that. This was a rigid body motion. Okay. And it has to do with that arrow that I showed you. So if you go back to the surface-based contact, right there, or yeah, if you go there, if you go to interaction, this line, see how these arrows are pointing in the same direction? They must be in opposite direction. You can't fool around with this guy, but this one, you click on it, it sends us down. Same direction. Okay? Run or simulate. I did not bother doing the model check and simulation check because I knew that those are okay. So let's see what happens now. This time, the plate, when it reaches the bolt or that cylinder, it establishes contact, it sees it, and it does not penetrate through it. So those things are important. There are some guidelines for selecting which one is the main surface, which one is secondary. The one that's rigid is more rigid, should be the, in our case, it's completely rigid, but for example, if it was aluminum or I don't know, aluminum and steel, the steel one should be the main one. Okay. As far as selecting those main and secondary entities, there are other ways of doing it. I went with, I believe, extrude and the inside hole, face of that hole, but could have been done differently. We're almost there. Plot when this thing reaches 1 means that the end of time has been reached and it stops. Okay, or you go to the iteration. That gives you more information in case there are multiple iterations to be done to go through that time increment. It records it here, number of attempts, severe discontinuity, or severe discontinuity due to different reasons. That's the last step, and then it's going to extract the results. Yep, extracting results. This time you're going to see that the plate stops at the cylinder. Stresses are going to develop. They're not zero right there. You can see that. Okay, so right there, you can slow it down. Go to this meter and choose a different speed. Speed. This is too fast, so we'll go here. Yeah. And incidentally, you can change the size here. Let me stop this for a second. If you double click on this dialog box opens up, and if you go to this tab, you can say also show me the elements. Shows you the mesh. Make sure you say apply. Don't forget to say apply at the bottom. There's something here that says apply. You can see the mesh pops up. And actually, let me show you the displacement here. For displacement, okay, you have to do the same thing. Unfortunately, double click on this, not the outline mesh, apply. But there's also something else that I want to show you, and that is this scale. Because the NLGeom because the NLGeom key was on, the scale is always set to uniform. If you want, you can set this thing to a larger scale. For example, I don't know, let's try 100. Apply, and you can see what happens. Terrible. So maybe 20. Apply. Yeah, that's more respectable. But anyway, NLGeom being on, it always defaults to scale of 1, and you can change it if you want. Okay, yeah, incidentally, if you look at this, notice that this didn't go all the way to 10. That's because we are stuck at this first increment. So if you select other increment, it goes all the way to 10. Good luck.